Hi, I'm Scott, and this is the Physics Project. And today we're going to talk a little bit about general relativity, one of my favorite subjects. It's one of my favorite subjects because it's awesome. It is so, I'm not, forget it. I'm not going to tell you, man. Forget it. You know what? I'm keeping it to you know what? Forget it. I'm not doing the take it all. I'm keeping it all to myself. You know what? Why not? We need two things to talk about general relativity today. We're going to need one of Einstein's equation that a lot of people are familiar with because we've heard it, but maybe haven't used it that much, E equals mc squared, and something that Gauss came up with that was applied to gravity that isn't seen that much, that basically says that if I have a certain amount of stuff, let's say mass, and it's sitting there, I can measure how much mass is there by standing far away from it and looking on how that mass pulls things towards it, like the Earth pulls us towards it, or the Moon pulls things towards it, or the Sun pulls things towards it. And if I surround this mass with a pretend surface, originally called a Gaussian surface, because Gauss is the one who figured the math out for this, that's not a real surface. But if I stand on that surface and test how much things get pulled in by this mass, and I do it everywhere, I do it at all points, and just keep going around, check out all points, I can find out how much mass is inside here. Notice I never have to look inside there. I can stand far away from it, set up an imaginary sphere, test everywhere on that sphere, and figure out what's inside. And that's the magic of Gauss's law. It works really well. We're going to use these two things and spend some time talking about gravity. I'm going to stop it and put some new diagrams on the board. And now I've got my diagrams. All right, check it out. I have a mass, right? Now, what it's got around it is a shell of mass that later I'm going to let collapse in on the original mass. Right here, I've got my Gaussian surface surrounding both of those masses, and if I do my test, stand out here and I see how much mass, how these masses pull inward. Believe it or not, Gauss's law works, man. This mass and these masses will all register as pulling mass in, even though this mass is completely contained in this shell. So this is like three-dimensional. I got a ball, and then I got a thick shell around it with some empty space in between. Even though this is completely surrounded, it still registers. And I will get a mass I find from Gauss's law, some amount of mass, m1. Right? Now here's what I'm going to do. I'm going to not just let it collapse. I'm going to reach in and mess around with it. I am going to, on the inner circle here, take negative charges and pull them away from their protons and move them to the inner sphere right there. Now those negative charges have almost no mass, but the electric field or pull from charges is huge. Give you an example. Person stands a meter away from me, I stand here. We increase the number of electrons on that person by 1%, the number of electrons on me by 1%, and then we see what the repulsive force of those two like charges is, and the force between us is enough to lift a person, a car, a mountain, or the Earth off of another Earth. Just to give you an idea, that's how I teach. I give multiple choice question, give you a second to think about it, then you talk about it. If you can find somebody to talk about with, if I was doing class, I'd have you talk in front of me, we talk it out as a group, and then we finish up on it. Take a second, what do you think? The answer is, it could lift the entire Earth off of another Earth. The electric force is that ridiculously strong. We don't see it that much because everything sits in a very nice balance around us, and we use a very minor change in that balance to make electrons flow through lights and basically create a lot of our technology. Anyway, I'm going to take those negative charges and I am going to take them off of here, off this edge right here, that inner edge, and move them to the center. So I end up with a bunch of negative charges on the outside of that inner shell and a bunch of positive charges on the outside, on the inside of the outer shell. Now, here's what's going to happen. Since I moved all those negative charges in, those positive charges sitting out, I end up with a field in between called an electric field. There is now this very strong electric field trying to pull those positive charges in towards those negative charges. This electric field is huge compared with how strong the mass of this is going to pull on the mass of that. Here's what we're going to do. We're going to let this thing collapse inwards. As it's collapsing, this mass out here is going to speed up and speed up and speed up and speed up and gain a ridiculous amount of kinetic energy. We are then going to have a magical machine. I'm not going to tell you how the machine works, but here's what the machine's going to do. It's going to take that energy that we get from having these things speed in and crash into this middle mass and convert it all into mass via this equation. Can that happen? Absolutely. That's what that equation means. Now that the mass has collapsed inwards, we're going to use our Gauss's law trick. Everything's sitting there, it's nice and fine, all the pluses and minuses are canceling each other out, all the extra mass that we created from E equals mc squared is there, and we are going to test how hard this pulls on stuff and find out how much mass is inside. When we do, we find M3. Here's the question. How does M1 and M3 compare? But notice, I'm not going inside. I'm just using Gauss's law from the outside. And here are your options. M1 is greater than M3. 2. M3 is greater than M1, or 3, M1 is equal to M3. And that's our first question. Gauss's law is just that good. Gauss's law will register the extra mass, and we will find that the extra mass does register and M3 is larger than M1. Let's try something else. Let's look at that middle step. I have moved the charges to the middle, right? There's all this electric field, I've done all that stuff. And now I'm going to use Gauss's law to measure how hard mass is pulled inward in this case. And when I do that, I will end up with the mass M2. The question is, how does the mass M2 compare with the mass M3? Now remember, I'm not looking inside. I am just standing out here and seeing how hard all the stuff in here pulls on any object I might put out at my imaginary Gaussian surface. And from that, I'm finding M2. Our second question becomes, how does M2 relate to M3? M2 is greater than M3. M2, let's do it the same way we did before. M3 is greater than M2. 3, M2 is equal to M3. If you do it, you end up with M3 equaling M2. Now this is a bit of a problem because it's supposed to be registering mass inside, and we know that this is more mass than this, yet here it's registering extra mass. Question is, where do you think that extra mass is coming from? What is it registering as extra mass? And that leads to our third question. A, or 1. The extra mass that is here, but not here, is coming from just this mass. Something I did when I did some of the charges, there is now extra mass here, and there is extra mass on this outer shell. So it's coming from the mass. 2. It is coming from the fact that there are plus and minus charges. The charges themselves, a charge by itself contributes to a gravitational field, it just acts like mass. Or 3, the electric field. What do you think? Answer is, believe it or not, electric field is a source of gravity. Electric field by itself, and I'm not talking about the charges, I'm talking about the field that exists between these two masses. That field actually contributes to the gravitational field. That field actually pulls things towards it. Electric field changes space and time, just like mass does. Oh, it's not just like, but it has similar properties. Anyway, and that is how we ended up with the extra mass. Here's another question for you. How did the mass, or how did the extra energy that is now contributing to the gravitational field get in the system? Because really what we're using here is this. Mass creates gravity, it pulls things inwards. Well, if mass and energy have an equivalency, you can make one into the other, that means that energy has to pull stuff in. Electric field has energy in it. That's what's pulling stuff in. Question becomes, how did the energy get into the system so that now this whole system is pulling harder inward? Your options are, the energy was introduced to the system in the collapse. The energy was introduced to the system when I pulled the negative charges away from the positive charges. No, 3, the energy was introduced to the system when I attached the negative charges to the inner shell. Think about it. The answer is, I put the energy into the system when I moved the negative charges away from the positive charges. They didn't want to go. I would actually have to go in there, pull them off really hard, and then as I built up more negative charges, these negative charges do not want to go there. They are getting pulled back by the positive charges. I put a lot of work or energy into the system, and that energy is registering from the outside as mass.